Okay. I'm scared. Well, anyway, let's hope for the best. So, thank you so much for being here. It was delicious, actually. We're gonna tackle section 4.2 today, okay? We're gonna study the derivative of a function, okay? So, how the derivative is linked to the behavior of the function, whether it's increasing, decreasing, or whether it's flat at a certain point, etc., etc. Okay? So oftentimes we've been talking about increasing functions. Okay? So, like, we have a sort of feeling about increasing functions, right? This is an increasing function. You're going up the hill. That's what it means, right? And as well, decreasing functions, they look like they seem to go down the hill, right? But you can do that plenty different ways. So, for example, you could go up the hill along a straight line, or this way, or this way, all right, or this way. Okay, so somehow we need to have a approach, okay, via the formula, via the derivative. Okay, so to try to understand what's going on here, because going up the hill along a straight line is not the same as going up the hill along a sort of complicated curve. Okay, so that's exactly the information that the derivative will provide us. And so, what's an increasing function actually? Well, think about, let me tell you here. Fix 2 points, x1 and x2, in the domain of a certain function, of a given function y equals f of x. If f of x1, which is this point down here, is less than f of x2, which is this point up there, or x2, the image, whenever x1 is less than x2, then we say that the function is increasing. Okay? So, suppose that a function is defined on the interval I, in this case, I don't know, an interval from 0 to probably 5 up there. Okay? F is increasing on that interval if whenever x1 is less than x2, then f of x1 is less than f of x2. That's the situation we depicted down here. Right? x1 is less than x2, and then f of x1 is less than f of x2. Clear? Okay, so the function is increasing. Right? Now, if the opposite happens, let me get rid of this table because if the opposite happens, so within the same interval down here, you choose x2 greater than x1, so x1 less than x2, but the function now at x1, so f of x1, is greater than the function at x2, f of x2, right? So x1 is less than x2, but now f of x2 is less than f of x1, then the function is decreasing. Alright? If that happens for all points x1 and x2, in the domain of the function or on a certain interval, right? Well, the function is increasing respectively or decreasing on that interval. Okay? So actually, increasing functions look like this, decreasing functions, they look like that. And now we have a mathematical way to describe that phenomenon down there. Okay? Do you understand? Okay. Are these permanent? This is permanent. I don't read Chinese. Is it permanent? I don't think so, right? But anyway. Anyway, thank you. Oh, it's Japanese. I'm sorry. Oh. Okay. I'm sorry. There's one more down here, but that one is not permanent, so I think that one is not, like, the right one is not permanent either. Okay, so see what happens when, let's check out, like, the figure up there. There are two figures, right? What happens when you have an increasing function up there? So my function is increasing according to the previous definition. x1 less than x2, then f of x1 is less than x2. This is increasing function. And down on the right here, we have a decreasing function. So what's the characteristic feature of that function on the left compared to the one on the right? So if you go back to the definition of the derivative is the slope of the tangent line to the graph at any point, right? So if you check the slope for any point in this interval, right, where that piece of graph is depicted, check any or fix any x there and compute the derivative. Well, you see that the tangent line has a positive slope. Positive slope, right? And on the opposite, in the case of a decreasing function, the tangent line has a negative slope. Alright? Because the tangent is downhill here, but the tangent is up the hill on the left. So if the function is increasing, the tangent lines have positive slopes. If the function is decreasing, then the tangent lines have negative slopes, right? So that's indeed a theorem, okay, a result. It's called the test for intervals of increase and decrease. So we suppose we have a continuous function on an interval I, okay, in a certain interval, fixed interval I, which is differentiable at the interior points of this interval. So we have a differentiable function on a given interval I, or A comma B, if you will. If the derivative is positive for all points of the interval, then f is increasing. Okay? So f prime positive implies that the function is increasing. If the derivative is negative, then the function is decreasing. So actually, this theorem is super cool because it allows us to compute actually the behavior computationally. Alright, we can obtain computationally the behavior of a continuous differentiable function on a certain given interval. Okay? How? Well, check the derivative. If it's positive on a certain interval, the function is increasing, right? If the derivative is negative, then the function is decreasing. So, positive derivative means or implies f increasing. Increasing there, okay? There, at those points where the derivative is positive. If it's negative, then the function is decreasing. Decreasing there. Do you understand? And that's a pure geometric reasoning. If the function is increasing, the slope of the tangent must be positive, because all the tangents have positive slopes. If the function is decreasing, then the tangent lines have negative slopes. Okay? So that's the first result, which is computational. Okay? So it allows us to do mathematics actually, and that's what we're going to do in example number 1. Is the microphone on? Oh, I'm sorry if I'm shouting. I don't want to touch anything there because I know it's going to crash. And then I don't want that to happen anyway. Let's check out this example number 1, okay? So we have a function here. We are given a function, no, we're not given any functions, right? We are given an interval, a definition of f. So f is continuous actually on the entire real line. Alright? But we're told actually, part 1, that f has positive derivative on negative infinity up to 0. All the way up to 0. Okay? So the derivative here, the derivative is positive. negative infinity to 0. Then from, on the interval 4, 6, down here, the derivative is positive as well. How can I turn down the volume? Do you have any ideas? Probably I should, where's the mic? I don't even see the mic. Hello? Where's the mic? Oh, I think it's down there. Hello, hello. Hello, hello, hello. Yeah, I don't want to touch anything. Okay, if it's like beeping too much, I'm going to lower down the volume. Okay, if positive on 4, 6, and then positive as well from 6 onward, 6 infinity, f prime is positive. Then the derivative is negative on 0, 4, so f prime is negative. And then f prime, so the derivative at 0 is not defined. And we're told as well that f prime at 4, so the derivative at 4 and at 6 is equal to 0. Okay. Okay? So we need to sketch somehow the function. So this is what we're going to do. So first of all, we're going to figure out what's going on with the super elementary graph. Okay? So what's going on there? So we're going to grab the interval of definition, in this case the entire real line, we're going to split into intervals over which we have some sort of information. And we do, because we know that from 0 to negative infinity to 0, derivative is positive, 4, 6 positive, 6 onward positive. Derivative 0 at 4, 6, and then derivative undefined here. But the function is continuous, okay? It's continuous. So the first thing that I'm going to do here, if the derivative is positive, I'm going to draw a line which is increasing. Okay, that doesn't mean that the function is a line. The behavior of the function is increasing down there. F prime negative means the function must be decreasing down there. And here, from 4 to 6, plump, the function must be increasing as well. When was it? Tuesday, on Tuesday, we had a theorem, right? If the derivative, like if we have a critical point, then by definition there, the derivative is either 0 or it doesn't exist at a critical point, right? Well, if the function is continuous, so we have 3 kinds of critical points there depicted. The first critical point look like this. So this continuity of the function at that point C. Okay? Clearly the derivative there doesn't exist because differentiable implies continuous. Alright? If the function there is not continuous, it cannot be differentiable, so the derivative there doesn't exist. Okay? Alright. So that's the first case where f prime C is not defined. Then we had 2 cases. We had a cusp point, or what do you call this? Sharp point, right? The derivative there doesn't exist because from the left, from the right, those derivatives don't match. Remember, the derivative is the slope of the tangent line. So you find one tangent from the left, you have another tangent from the right. They don't match. Okay? They're not equal, so no limit there at C as well. So doesn't exist. And then there was yet another case where the function looked like this. So we had sort of vertical derivative down there. So f prime at that point C doesn't exist either. In this case, particular example, we know that the function is continuous. So this example down here, this situation down here doesn't hold. Okay? Well, yeah, that's fine. Alright? Because the function is continuous. So the only situation is that we have something like this or something like that. Alright? So with this information, with this configuration, if you will, now we can depict, we can sort of sketch the function. We know, by the way, we know that the derivative at these 2 points is 0, meaning the function at 4 and at 6 is like tangent to the horizontal down there. Okay, so the derivative is horizontal at 4 and at 6. So let's see what we can do. So from negative infinity to 0, we have a function. Do we have any zeros or not? I think we don't have any zeros. Alright, we don't have any zeros. I mean, they didn't tell us. They did not tell. They didn't say anything about zeros. Okay, so the thing is that at 0, you go from increasing to decreasing, but also the derivative here is not defined. So since the function is continuous, you are increasing and then decreasing from the other side of 0. So this situation is not, it doesn't happen. Because in this case, you come increasing from the left, but you go increasing from like the right onward. So you are increasing here around C, around the point C. So this situation doesn't hold either. So the only situation left where the derivative is not defined is a sharp point. So there's a sharp point at x equals 0. So the function is increasing, there's a sharp point down there, and then it's decreasing all the way down to 4. So it's decreasing, so probably it looks like something like this. At x equals 4, the derivative is 0, meaning this point here, like the tangent at x equals 4 is flat, it's like horizontal. And then you're increasing. At x equals 6, you probably have a saddle point, like x power 3, y equals x cubed, right? Because you're increasing from one side and then you keep increasing from the other side. So at that point, you have probably a saddle point at x equals 6. So this is a very rough graph of the function. I mean, this is not an accurate graph of the function. It's a first approximation, if you will. Okay, so there's a cusp point here, a sharp point, for sure. The function seems to be like flat at x equals 4. I don't know what's the value of the function though. Okay, I don't know whether the x graph is passing through the function like this or not. I don't know, because I don't know any information about the zeros of the function. But that's pretty much the shape. So let's check out what we get. Oh yeah, so I mean, it looks like the function we depicted, but we need more information, okay? To be able to depict the function accurately, we need information about the second derivative, okay? So that's at the end of the lesson, our lesson today. But this is a first approximation to the graph of the function, all right? Is it clear? Right, let's move on. And let's check example number 2. Take example number 2. Find the intervals of on which the following functions f of x equal x exponential of negative x and f of x equal 2x cubed plus 3x squared plus 1 are increasing and decreasing. Okay? I'm going to do it on this side, okay? So we know that f prime positive implies that the function is increasing, f prime negative implies that the function is decreasing. So let's grab the first function down there. Let's study the first function. So this is example number 2. Let's compute f prime of x. Product rule, you have exponential of negative x plus x times the derivative of exponential of negative x. This is negative exponential of negative x. Okay? So that's your derivative. Now look, if you factor out the exponential of negative x, you get 1 minus x. Now obviously this function is defined, like the domain of this function is the entire real line, right? Minus infinity, positive infinity. And this term down here is never equal to 0. So if we assume that derivative is 0, it means that 1 minus x is equal to 0. Meaning that x equal 1 is the only, x equal 1 is the only critical point there, isn't it? Right. So now, we have two situations here. We have 0, and 0 splits the real line into two subintervals. We need to check whether the derivative is positive or negative on the left of 0, and whether it's positive or negative on the right of 0. Okay? So how are we going to do that? Well, x equal 1 is the only critical point down here. Sorry, not 0, but 1. Okay? So that means that if you, like, right before hitting 1, the function doesn't change its behavior. So either it's increasing all the time on the left of 1 or decreasing all the time. And the same thing happens on the other side, because this is the only point where the derivative is 0. So there's no change of the sign of the derivative before hitting x equal 1. Do you understand? Because if the derivative changes sign, we would have another point here, another critical point. Well, that's not the case. There's only one. So either f prime here is positive at all times for all the x's, right? Or negative for all the elements on the left of 1. And to the right of 1 onward, right, the derivative is either positive or negative as well for all the x's to the right of 1. Okay? So what you can do here is pick one element, say x equals 2, and evaluate f prime at x equal 2. Alright? So note here, note that f prime of 2, what's the value of f prime of 2? It's the exponential of negative 2, 1 minus 2, so this is minus the exponential of negative 2, and this is negative. Okay, so the derivative here is negative. For all points less than 1, for all the x's less than 1. And what about the derivative? Sorry, 2 is right here. 2 is right here. So the derivative is positive. The derivative is negative down here. Because I've taken x equal 2. I plugged x equal 2, which is to the right of 1. So the derivative is positive down there. So now we need to take an element to the left of 1, 0, and evaluate it. So f prime of 0 is equal to exponential of 0 is 1, and then 1 minus 0 is 1. It's 1, so it's positive, exactly. So the derivative here is positive for all the points. I think this is permanent, but anyway. Okay? Thus, the function here is increasing, and past the point 1 and onward, the function is decreasing. Okay? So let me use this little slot here, hence f is increasing on negative infinity 1, and it is decreasing on 1 plus infinity. Now, these people have depicted the function down here. I think this textbook is super confusing because they include too much unnecessary information. So, for example, here we don't need the derivative, the pink curve down there, that's redundant because we have the sign there, okay? So don't look at the pink graph down there. I think it's awful. It's an awful text. But anyway, we have the black curve down there, and that's our function actually, f of x. X exponential of negative x. Well, before you hit x equal 1, you're clearly increasing. But past 1, you are decreasing. That's what the derivative tells us. Okay? Now, again, it's a rough idea that you get from the first derivative. So to get an accurate picture, right, a figure which accurately reflects the graphical function, you need a second derivative, but that's later on, okay? So we need to wait a little bit. A second example down there. I'm going to clean up on this side, okay? So let's go quickly. It's fine. Do you have any questions? Is it clear? Right. If you have any questions, raise your hand, let me know, okay? So the second function is a polynomial, actually a cubic polynomial, f of x. F of x equal 2x cubed plus 3x squared plus 1. Okay. Let's compute the derivatives right away. So f prime of x equal 6x squared plus what? 6x plus 0. Alright. Polynomials are good behaved, okay? So they are C infinity, they are super differentiable. Super differentiable. So for sure there's no point at which f prime is undefined. It's always defined. Because the derivative of a polynomial is another polynomial. And the domain of the polynomial is the entire real line. Okay? So there are no bad points for the derivative. No like critical points where the derivative is undefined. Alright? But f prime equal to 0 means, so here we factor out by 6x and x plus 1 equal to 0. And this means actually x equals 0 or x equal exactly minus 1. So let's see what we get now, because we have two critical points at 0 and sorry, the other side, negative 1. Right, so we're gonna, like, you cannot pick these two, like, neither of these 2 points, because if you do, f prime at those points is 0, okay? So you need to take any point to the left of negative 1. For example, you can take negative 2 and take the sign of the derivative of negative 2. So let's take it out. F prime of negative 2 is 6 times 4 minus 12, isn't it? Isn't it? So that's 12. That's positive, right? So f prime here is positive. F prime here is positive. What about the interval negative 1, comma 0? We need to grab here one point. What point? I don't know. Yeah, they grab negative 1/2. So we're going to take negative 1/2 down there. And we're going to compute f prime at the point negative 1/2. So we're going to get 6 negative 1/2 squared, so 6 divided by 4. And then minus 6 divided by 2, that's 3. Right? So you get here, that's negative actually. That's actually negative. Okay? The 6 minus 12, that's negative 12 divided by 4. Isn't it? Negative. So f prime here is negative. And then what happens to the right of this point, the critical point 0? Let's take 1. So f prime 1 is 6 plus 6, 12. Again, positive. Okay? So f prime here is positive. Thus, your function looks like, well, it's increasing from, it's increasing from negative infinity to negative 1. Then it's decreasing from negative 1 to 0, and then it increases again up to infinity. Well, it increases up there. Will the function ever go down again? Like decrease? Will it ever go down? Like, will the function do this ever again? Why not? Because if it did, we should have detected a critical point here. That critical point, but we didn't. There's only 2 critical points here. Negative 1 and 0. So the function actually, it's increasing, so it must be either asymptotic to some horizontal asymptote or increase up to infinity. Okay? But there's no other critical point down there. And I think these people also graph the function. Yeah, it's that up there. See the black curve down there? So you have a critical point at 1 and the point 0, which is up there. Derivative positive, derivative negative, derivative positive. So increasing, decreasing, increasing. I think this is fun. I mean, this is super interesting. It's interesting, right? Because you have a computational way now. By the way, this is what your calculator, your device is doing actually. Okay, when you plug in a function, the device, your calculator or your phone, they first of all compute the first derivative. They compute the second derivative for a reason that we're going to talk about in a few minutes. And then they compute y intercepts, x intercepts, and then they trace the, they plot the function actually. But this is what they're doing, those devices actually. Good. So that's the next question. How to identify local maxima and minima. So we identified last class global or absolute minima and max, right? So we computed, if you're given a continuous function which is differentiable on a certain interval, you compute the critical points, you evaluate the function at the critical points and at the extreme points of the interval a, b, a comma b. So f of a and f of b, and compare the values of the function at the extreme point. And at the critical point, you choose the min and the max. There may be more than one min, so more than one minimum, more than one maximum as well. Okay? But those are global. You're choosing their global. So how to identify actually local stuff now, local extreme points? Well, actually, this is super fun. It's much fun. Look. There's a theorem down here which is called the first derivative test. And if the function, suppose we have a continuous function, right, with a critical point c, such that the function itself is differentiable around c, around the point c. If the derivative changes sign from positive to negative, then this critical point here is a local maximum. Alright? That's what the theorem says down there. If the derivative changes sign from negative to positive, the derivative, then the function has there a local minimum. Derivative negative means the function is decreasing. Derivative positive means the function is increasing. But it's continuous. So these two branches are like they are glued together there. They match at that point. So there must be a minimum there, local minimum. Okay? Now if f prime is positive on both sides or negative on both sides of your critical point, there's no extreme value, no local extreme value. So there's a saddle point down there, okay? So if the derivative at a certain point is 0, you have a critical point. If it's decreasing from one side, right, and then it keeps decreasing from the other side, most probably there you have a saddle point. So y equal x cubed, or like pretty much like the same thing but decreasing. If f prime is negative from both sides of a critical point, you have probably a saddle point down there. Okay, so you don't have a local mean or a local max at that point. We're not going to prove this theorem, okay? So we're going to solve example number 3. Excuse me. It's too humid for me. But anyway, let's see what happens there. Let's check this one out. Let's check this example out. Any questions? Okay. Example number 3. Example number 3. consider the function f of x equal 3x cubed, 3x, power 4 minus 4x cubed plus, minus 6x squared, 6x squared, and then plus 12x, and then plus 1 down there. Find the intervals in which f is increasing and decreasing, and then identify the local extrema of the function f. So, like your reflex at this point should be boop, compute the derivative automatically. So f prime. F prime of x, what is it? 12x cubed minus 12x squared minus 12x plus 12. Right? Now, of course, here you can factor 12 out and you get x cubed minus x squared minus 6 plus 1 down there. And this is equal to what? 12 and then x cubed, x squared. You can take the x squared out, so you get x minus 1 minus, and then this term down here is the same as x minus 1. Thus, you get 12 x squared minus 1 x squared minus 1 times x minus 1. Is it minus 1? Yep. That's fine. Okay, so this is 12x minus 1 squared times x plus 1. Because x squared minus 1 is x plus 1 x minus 1. X minus 1 times x minus 1 is minus 1 squared. Okay? Right, so equal to 0. Again, polynomials are super cool because their derivative is always defined. It's another polynomial. So you don't have bad points where you have like you go to infinity or undefined points or critical points where the derivative is undefined and stuff like that. You know what I mean, right? Like the derivative of a polynomial is another polynomial. Super smooth, right? You can differentiate it infinitely many times and you get a continuous function every time you differentiate it, right? So there's no point where the derivative explodes. It blows up to infinity. Or it's undefined. Or cost points. No, because the derivative of a polynomial is smooth. It's differential. It's continuous. More than continuous, it's differential. It's smooth down there. It's a little bit too humid. Anyway, critical points here. So critical points at x equal what? What's the first critical point? 1. And negative 1. Well, negative 1 and 1. 0 is, by the way, no critical point here. Okay, so again, what you have to do, you locate, you place those critical points on the line. So negative 1 here, positive 1 up there. So derivative on the interval negative infinity, negative 1. You must choose one point down there, right? So say negative 2, negative 2, plug it in, negative 2 here, you get positive. So this term is always positive. But negative 2 plus 1 is negative 1. So this term is negative. So f prime here is, f prime is negative. Very good. From negative 1 to 1 you have 0. down there. Plug 0 in, positive. 0 plus 1 is positive. So f prime here is positive. And past 1, you have 2, for example. At that point 2, you get positive, positive. So f prime is still positive at that point. So the function is decreasing down here, but increasing, and then increasing. It keeps increasing down there. So here, you have a saddle point. You don't have a minimum or a max.
So what's the point of the
Huh?
What's the point of the y?
This critical point? Okay, so remember that on Tuesday, we studied the function y equals x cubed, right? We said on Tuesday that a function, like if f prime at a point is equal to 0, it doesn't imply that that point is a minimum, local minimum, or local maximum. Like in this case, okay? Because you have y equals x cubed, it looks like this. Okay? What is the derivative of x cubed at x equals 0? At that point, you get f prime at 0 equal to 0.
So what's the points mean?
It's saddle. I called it saddle point. Saddle point. Saddle means you keep increasing, well not actually, but pretty much that's the idea. You keep increasing all the time or decreasing all the time, even though the derivative is 0. It comes from the cowboy, you know, the westerns. The saddle is, you know, the thing you're sitting on a horse when you're riding the horse and stuff. That's a saddle. So it looks like convex from one side, and from the other side it looks like concave. So if you cut it along, you find some of this. Okay, this kind of curve. So that's why it's called a saddle point. But don't worry about that. Alright, so we have here at that point a -1 is a local minimum by the theorem, because from the left you are decreasing, from the right of it you are increasing, and the function is differentiable and continuous. Okay, so the function at -1 must match. I mean, these two branches match at that point. They are not discontinuous. The function is continuous. This function is super continuous. Alright? These two branches indeed match at that point. So you have a local minimum. Okay? So by theorem, I don't know, theorem 4.3, x equal -1 is a local min. X equal 1 is neither a log min nor a log max. It's not local minimum, not local maximum, because the derivative doesn't increase. I mean, it doesn't change sign. It's falling to the left and to the right. Okay. See, so f doesn't have a local extreme value at x equal 1. Indeed, the function is depicted down there, up there, in black curve down there. So at x equal -1, local minimum. At x equal 1, there's no local extreme value. That's a saddle point. Okay? Alright. Any questions? No? Let me tell you quickly about this example, alright, because it's pretty much the same thing we did before. This is it's not a polynomial. The derivative is depicted down there. So let me tell you about this example. So here's the function actually. Okay? So let's do this quick because I need to jump into the second derivative today actually. So today we're done at 11:45, right? Okay. Right, so let's study this function down there. G of x, x power 2/3 times 2 minus 6. G prime is super easy to compute, right? We did compute this like the derivative last class. We computed the derivative of this same exact function. So the derivative is up there. We factor out by x power -1/3 divided by 3. So you actually get 4 minus 5x divided by 3 times x power 1/3. That's the derivative. Well, the bad news here is that now we have a critical point where the derivative is not defined. Okay? So we have two classes. Well, we have one point, x equal 4/5, one critical point where the derivative is 0, one critical point, x equal 0, where the derivative actually is not defined. Okay? Now, this is the plot we obtained last class. At 0, the derivative is not defined. At x equals 4/5, down here, the derivative is 0. See? G prime here of x, well, G prime of 4/5 is equal to 0. So the function is flat at that point. Alright? The tangent is flat at that point. And then we have a cost point at 0. This function is not a polynomial, so it may not, it's not smooth. May not be differentiable at certain points. Well, at 0, this function, right, the derivative is not differentiable. Okay, we find here the cost point. But nevertheless, we can study the sign of this derivative via the table. So we split the domain of this function at 0 and then at 4/5, which are the critical points. Take here a point to the left of 0 and plug it in. So for example, -1. Okay? So -1, 3x power 1/3, this is negative for sure. So the denominator is negative. The numerator is positive. Positive, because -1 here with a negative sign, you are positive. So 4 minus 5x is positive, denominator negative, meaning g prime derivative is negative. Between 0 and 4/5, you grab here any point. 1/2, for example. No, 1/2. 1/2. Yeah, 1/2 is down here, right? So plug it in. What do you get there? G prime of 1/2 is 4 minus 2.5 here, positive, divided by 3x 1³ at x equal 1/2, so this is positive as well. So positive over positive, G prime is positive. And you can verify to the rate of 4/5, and you get negative over positive, so G prime is negative. Thus the function here is decreasing. G prime positive means the function is increasing. G prime negative means the function is decreasing. So it looks like this. Theorem 4.3. Derivative negative, derivative positive. You have a minimum at that point. Local minimum. Derivative increasing, function increasing, function decreasing, you have a local maximum at that point. Because it's continuous at those points. Understand? Alright. There you have it. I need to step into the second derivative down there. By the way, an observation here. This is just an observation. Actually, it's theorem 4.4 here, not 4.3. 4.4. Observation: if you find only one local minimum on a certain small interval, only one critical point which is a local minimum or a local maximum, then that local min or local max is an absolute min or an absolute max on that interval. Okay, so that theorem says basically one extreme point, only one extreme point on a certain given interval, it must be the maximum on that interval down there or the minimum on that interval. Don't worry too much about that. Okay? This is exactly what I was talking about before. Look, if you have an only local minimum on a certain given interval down there, it must be the local minimum of the function on that given interval. It must be the absolute as well. Because if the function had another critical point, if the function had another maximum, for example, or a minimum of that interval, then there would be other critical points, and there's none, because we're assuming that there's only one on that point. Okay? So that's why we dig down here. If the function past the point 1 here, for example, is increasing, then it's going to keep increasing forever. Okay? Because if it doesn't, then there should be a critical point somewhere. But we didn't detect any additional critical points. Okay? Much better. Okay? So, let's talk about the concavity and the inflection point. This is actually what will complete the picture in this chapter, okay? So, after we study concavity and inflection points, then we will be able to actually accurately draw the graph of the function. Accurately. Okay? With all details, whether the function looks concave or convex, and stuff like that. Right, so check out that function up there. Well, the graph of the function up there. The function is increasing at all times, right? It's an increasing function. So the function from negative infinity to 0, let's suppose that's 0, the function is increasing. At the point x equals 0, the derivative is 0 as well. Okay, so there's a critical point actually at x equals 0. But after 0, so from 0 onward, the function keeps increasing. But I don't know if you noticed, the way the function increases from the left, like from negative infinity to 0, is not equal to the way the function increases from 0 onward. Something's going on here. So let's check the left-hand side of the function, this right hand here. What happens with the derivative? What happens with the derivative down here? Huh? Yeah, the derivative, exactly. The derivative is positive at all times. So f prime here is positive. Function is increasing. But the derivative, the function derivative, like she says, is approaching 0. So here is super positive, then not much positive, and then all of a sudden it turns 0 here. So the function derivative is actually decreasing. Okay? The function derivative, this function is decreasing. Because it's super positive here, super positive, then positive, but it's decreasing. It's getting to 0. So that means that the derivative of the derivative must be negative. Because the derivative function, even though it's positive, the derivative is decreasing. So if a function is decreasing, its derivative is negative. Alright? That means that the second derivative is negative. What happens to, like, from 0 onward, from 0 to the right? Well, the derivative was 0, and then all of a sudden, it starts increasing. So this function derivative, or a g, is increasing. As it was 0, then it started being negative, sorry, positive. Suddenly positive, and then positive, and then it's super positive up there. For this point, the derivative is super positive. So this function g is increasing. So the derivative of g is now positive. This is a way in mathematics of saying that the function is concave down or concave, and f double prime positive is a way of saying that the function is convex or concave up. Okay? So a function that looks like this is called concave down. okay? Concave down, or simply concave. Some people call it concave, okay? So they look like this, like sat. And they look like this when the second derivative is positive. Those kind of functions are called concave up. Concave up. Or convex. Some people call them convex. So this branch, the left-hand side of this graph is concave down, meaning the second derivative is negative. Past 0, the function turns happy. The function is concave up, or convex. So convex, happy means if double prime positive, second derivative positive. Sad means concave down, or concave, the function is, the second derivative is negative. Okay, so don't forget happy if double prime positive, and sad if double prime negative. Concave up or convex, concave down or concave. Okay? So the second derivative actually measures, right, how happy is the function, if you will. Alright? Now one thing, look, when the function is sad actually, right, the tangent line is always on top of the function at any point. So fix that point up there. See, the tangent line is always on top of it. So when the function is sad, the tangent line is always on top of it at any point. When it's happy, right, like so, then the opposite happens. Right? The tangent line is always below the line at all points. So that's one way to view it as well. And for me, I think this is the easiest way to retain it. Because now we have a clear picture about, like, you can increase in two possible ways. You can increase happily, but also you can increase in sad way, right? You can decrease happily, or you can decrease in a sad way. So two ways of decreasing. So the first derivative actually does not tell us whether the function is happy or sad. The first derivative. So we need to like take one step further, right? And use the second derivative to accurately get the graph of the function. So let's see what can we do in this case. There's actually here a definition. And this is the actual definition. If a function is differentiable of an open interval I, if the function is increasing, then the function is concave up. If the derivative of the function, if f prime is increasing, like the derivative of the derivative is positive, then the function is concave up or convex. If f prime is decreasing, meaning that the second derivative of the function, right, is negative, then the function is concave down. If the function is continuous at a point and changes concavity at that point C, then that point is called an inflection point. You've heard this term before. Probably in meteor, I don't know, what do you call that, in environmental sciences and stuff like that, they talk all the time about inflection points, right? Climate change and all this stuff, they talk about inflection points. Sometimes they have no idea why, but they talk about it. Well, this is the reason why. An inflection point is where the level of happiness of the curve changes. Okay? So you go from sad to happy, well, that's an inflection point down there. Alright? Y equal x cubed. Well, 0 for y equal x cubed is an inflection point actually. So you go from happy, sad to happy. Okay? So let's solve a few examples because we need to get to actually compute. Like we need to get a computational way of doing or classifying these kind of curves down there, according to concavity or whether the curve is increasing or decreasing. So theorem 4.6 This is the second most important test. First test was the first derivative test. Okay, if the derivative f prime on the left at a certain point is positive, the function is increasing, and if it's negative on the right at that point, the function is decreasing, thus you have a local max there, a local maximum, and vice versa, okay? But there's yet this theorem, and this is the test for concavity. So suppose that the second derivative exists, okay, on a certain interval I. If the second derivative is positive, then the function is happy. It's called or convex. If the second derivative on that interval is negative, then the function is sad. Okay? 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 Alright. If C is a point, right, at which the second derivative changes sign, so you go from positive to negative or negative to positive, that point is an inflection point. Okay? The function has an inflection point there. Now look, very, very important remark right now. See, on Tuesday, right, we established the following fact. If you have a local minimum or a local maximum of a continuous function, right, differentiable function, then the derivative there is 0, right? Like flat, like horizontal tangent, derivative 0, log min or log max. However, if f prime at a certain point is equal to 0, then the function need not have at that point a log min or a log max. For example, y equal x cubed at 0. At 0, that function doesn't have a log min and it doesn't have a log max. So the same phenomenon happens here with the second derivative. Okay, some points to keep in mind. The fact that f double prime at c equal to 0 does not imply that we have an inflection point there. Okay? We may have a function which is happy, and then at that point you have second derivative equal to 0, and then it keeps being happy afterward. Or it may be sad, you have an inflection, not an inflection point, you have second derivative at that point equal to 0, and then onward, after that point, the function keeps sad all the time. So f double prime equal to 0 does not imply that c is an inflection point. Keep it in mind, and don't forget about that. So there's a good example about this situation f of x equals x power 4. X power 4 looks like this. It's like a parabola, but it's super flat here around x equals 0. Okay? So this parabola actually doesn't have an inflection point there. So f double prime of x, so f of x equal x power 4, f double prime is for sure 24x, right? Let's do it. F prime equal 4x cubed, and then f double prime should be 12x squared, sorry. 12x squared. Thus, f double prime at 0 equal to 0. Is 0 an inflection point? No. However, x equals 0 is not an inflection point. Inflection point. Because the concavity doesn't change. It's happy all the time there. Happy and then happy. So f double prime here is positive, and f double prime here is positive as well. Happy all the time, but 0 is not an inflection point. Okay? So, gotta be careful there. F double prime equal to 0 does not imply that the point is an inflection point. It does, the function may not change their concavity at that point. Okay? Now, typically, if the function has an inflection point, then the derivative, the second derivative is 0. Okay? However, an inflection point may also happen at a point where the second derivative does not exist. Just like a critical point is a point where the first derivative is 0 or it doesn't exist, an inflection point is the point at which the second derivative, 0 or it doesn't exist. Do you understand? So critical points are related to the first derivative, just like inflection points are related to the second derivative, the same way. Okay? Something for you to meditate on when you get home tonight. You focus on this lesson. Okay? It's going to be available on YouTube. If you want to go back to it, you can do that. All right? Any questions? All right, let's move on because now we need to do some computations actually here. Okay? If you have a question, let me know. Right, so back on in Tuesday class, right, we had the 4 situations for a critical point. So the function wasn't continuous at a point, thus the derivative didn't exist at that point, or you had a cost point, so the derivative didn't exist, or there was a vertical line there, thus the derivative doesn't exist, or the first derivative was equal to 0. Okay? There are 4 cases here as well. So if double prime equal to 0, you may have something like a saddle point down there. Okay? The concavity in this first case changes. See, because the function is sat to the left, but it's past the point C to the right, the function is now happy. So the concavity changes at that point. So that's an inflection point actually. Now, in this case, which looks like the previous case of f of x equal x power 4, here the concavity doesn't change, but still the second derivative is equal to 0. Okay? So x equals c in this case is not an inflection point because the concavity doesn't change. The function is happy at all times, to the left and to the right of x equals c. Let me check the still recording. Yeah, I'm still recording. That's fine. Sorry about that. Okay, so no inflection point down there. What about this situation? Well, point x equals c. Clearly here the second derivative doesn't exist because you have a vertical line down there. So the first derivative doesn't exist. The function there is not differentiable. Okay, you have vertical tangents at that point. Okay, the function is concave up to the left, but it's concave down to the right of that point. Thus, even though the second derivative doesn't exist, x equals c is an inflection point for sure. Okay? And last situation, clearly here the second derivative doesn't exist because we have a cost point down there. So second derivative doesn't exist. The function doesn't change concavity. It's sat and it's sat. Alright? So concave down to the left, concave down to the right. The function doesn't change concavity. This is not an inflection point. Alright? So whether a certain given point is an inflection point or not depends on the graph of the function. Alright? If double prime of c equal to 0 is a candidate, okay, gives you a candidate for an inflection point, or if double prime at a certain point c doesn't exist, tells you that x equals c is a candidate for an inflection point, but it may not be an inflection point like so, like this one up there. Okay? Okay, so let's, with all these ideas, we can now, I think we can, okay, let me tell you something very, very quick about example number 6. Look, this is the first approximation to sketching functions, okay? So, example number 6, number 8. Try to sketch a function which satisfies each set of conditions on some interval that we have to choose. Well, a f prime positive on that interval, and f double prime of t positive as well. And then part B, g prime positive, but the second derivative, g double prime of t negative down there. Okay. What does f prime t tell you about, like, whether the function is increasing or decreasing? So this condition tells me that the function goes upward. What about that one? Is it happy or sad? It's happy. It's concave up or convex, right? Convex or concave up. Let's use the other denomination, concave up. This is happy. What about G? G prime positive means it's increasing, and G double prime negative, it's going to be sad. Concave down. Concave down. See? So you have two situations here. You have, on the one hand, one function which is increasing, but it's happy, and you have the case of a function which is increasing, but sad. So you could be increasing in a happy way, or increasing in a sad way. You understand? That's the information provided by the second derivative. It tells you whether the function is bent down or bent up. Happy or sad. Do you guys understand what I'm saying? Is it clear? Are you sure? Any questions? Ladies, any questions over there? Alright. Super simple sketch. Now, the function may be, like, if the first derivative is negative, well, the function would be decreasing. But you could be decreasing happily or in a sad way, right? Well, happy decreasing, it's like so, or sad decreasing is the other way around. Now, we need to sort of, we need to put all these conditions together into the graph of a function. So we need to keep in mind all these conditions in the next chapter, okay? Let me check something out here. Okay, only 2 more pages down there. Right, example number 7, detecting concavity. In this example, we need to identify the intervals on which these functions are concave up or concave down, and then locate the inflection points. Okay. Do that quick. Again, if you have any questions, raise your hand, let me know, and I'll try to answer your question. Okay? Example number 7. Let's work out the first function down here. This class was a little too long, okay? Because there are way, like too many concepts we need to study. The next class is a little shorter because actually it's focused on computations actually, right? But believe me, the first step is to understand. If you don't understand the concept, then you won't be able to solve the problems. Okay? It's very important to understand what you're doing actually. Example number 7, part A. Actually, I'm going to compute right away the second derivative. So f prime of x, it's the same function. So we get 12x cubed minus 12x squared minus 12x plus 12, right? Plus 12, isn't it? Minus, yes. So the second derivative is 36x squared minus 24x plus minus 12. Right, so this is actually 12. Right, so how can we split that into, can we split this thing into two monomials there? Oh yeah, it's down there, it's x minus 1, and then 3x plus 1. There. Right? So for candidates, okay? Candidates of an inflection point, right? For inflection points, well, we have 2. We have x equal 1 and x equal negative 1/3. Excellent. And we're going to do exactly the same thing we did before. We're going to split the line, because this function is defined on the entire real line, right? So it's defined on minus infinity plus infinity, because it's a polynomial. They are super smooth everywhere. And then we're going to split the line into these 2 points, 3 parts, right? Determined by negative 1/3 and then positive 1. Quickly, you're going to do the exact same thing we did before. We're going to pick one point, say -1 here. You take -1 and you evaluate f double prime at -1. You get actually here negative and then negative. You get positive. You're positive here. And then so f double prime here is positive. In between you have 0. So f double prime at 0 is negative. So f double prime here is negative for sure. And then on 1 onward, you can pick 2, for example, f double prime at 2, you are for sure positive. So f double prime here is positive. So the function, so what are you going to do now? Well, determine whether the function is happy or sad. If double prime positive, the function is happy, sad, happy. Meaning you change concavity actually at -1/3 and x1. So both points are actually inflection points. Do you guys understand? Ain't that cool? Is it cool? It's nice, right? Thus, both x equal -1/3 and x equal 1 are inflection points. Okay? And I think that's depicted down there. See, look, the function looks like the black curve down there. So it's bending upward, it's bent upward, then it's bent downward, and then it's bent upward past 1. Both points, -1/3 and +1, are thus inflection points. Okay? The arc sine, guys, let's discuss quickly part B, the inverse sine of x. Do you have any questions here? No? Okay. So part B, f of x equal sine minus, well, the inverse sine of x on the interval -1, 1. On that interval, remember, the arc sine is injective, actually. Okay? So, sorry, I'm a little tight. So f prime of this thing, f prime of x, derivative of the arc sine was 1 over, I forgot, 1 over the square root of 1 minus x squared, right? And then the second derivative, you need to work out the expression a little more. It's not hard to do. Yeah, so the first derivative is up there. And then the second derivative, don't forget to apply the chain rule down there. You're going to get -2x. Well, I'm sorry, I'm so tired. You get x over 1 minus x squared power 3 over 2. I'm tired. It's too hot here. Oh, you're freezing over. Is it too hot? It's hot here. I can't stand humidity. I hate it. It's like, but it's not bad actually outside. It's just a little. It's a little humid, but it's not hot. Like when you have 40 degrees and it's raining. Oh. No, I need to get out in the summertime. I was working in the UAE before, and I'm in Dubai there. That's 50 degrees summertime. 50 degrees, 90% humidity. You're like, you don't want to move. It's disgusting. It's disgusting. Yeah. The weather there is horrible. Anyway, let's compute now. Okay, look. F double prime equal to 0 at what point, actually? F double prime equal to 0 at what point? X equals 0. And then f double prime, we have here a problem. F double prime, that does not exist, right? Does not exist at x equals 1 exactly. If you evaluate this expression at 1, you get 1 divided by 0. Does not exist. So these two people down here are candidates for These are candidates for inflection points, right? Inflection points. But we need to prove now that they are inflection points, so we're going to do exactly the same thing. So, am I missing something? Negative 1 as well. Negative 1 as well, I forgot that one, right? Because if you plug in negative 1, 1 minus negative 1 squared, which is 1, you get 0. So I was forgetting that one. So it's negative 1. No. These points don't belong in the domain. Because the function is not defined at 1. So these do not belong in the domain of our function f. So out, kick them out, okay? So we only have one inflection point. Candidate for inflection point is only x equals 0. Nothing else. So we need to check whether the function f double prime here is positive or negative. And we're going to choose the point negative 1/2, for example, which is down here, negative 1/2. Plug it in. Negative 1, well, this is always positive on that interval, right? And the top is negative. This is negative actually here. And if I plug 1/2 on the other side, it's going to be positive. So actually, is it happy or sad here, the function? It's going to be sad, and then happy. So do you have an inflection point down there? Thus, x equals 0 is the only inflection point. Okay. Go left. There you go. And actually, that's the graph of the function. The only inflection point here is 0. The function is sad, see? Concave down. But then past 0, it turns happy. Concave up. So inflection point x equals 0. Is now something super cool to compute actually log mean and log max, local minimum and local maximum. Local minima and local maximum. So if this, well, suppose that the function is continuous and it's you can differentiate the function at least twice, so f double prime is a continuous function. If the second derivative at a point C is positive, then the function has a local minimum at C. If the second derivative is negative, then the function has a local maximum. And if the second derivative of the point is equal to 0, then the test is inconclusive. You can't tell whether you have a min or a max at that point. Okay? So again, second derivative at a certain point. I forgot to tell you, the first derivative must be 0. So this point is a critical point. Okay? So if the second derivative at a critical point is negative, you have a log max. If the second derivative at a critical point is positive, you have a log min. Yep, a log min. Okay? So how to implement this? Actually, we're not going to prove this. How to implement this theorem? But let's check it out. Take this example. I think this is the last result. For this section, I know it's the section, like we visited way too many concepts today. It was like not easy. But over the next section is going to be much easier. This is going to be computation. Okay. You need to understand first and then try to solve the problems. Okay? So let's solve this problem down here. Example number 8. Use the second derivative test to locate local extreme points for those functions up there. Okay? I'm so tired, I don't think I'm going to teach in the evening because I have recorded the lesson, so I'm going to give them the link. I'm going to go there just in case, and I'm going to explain because I have the slides, I have the text on the slide, but I'm so tired I won't be able to explain this thing from scratch. Okay, anyway, first derivative for this function, f prime of x, so this is part A. Again, same example, 12x cubed minus 12x squared minus 12x plus 12, right? And then second derivative here is 36x squared minus 24x minus 12 down there. And then we had the critical points, right? Critical points here. How do we compute critical points? F prime equal to 0. That's the equation for critical points. Okay, so I need to equate this polynomial to 0. Hold on. Yeah, it's fine. So that means 12x cubed. Actually, I'm gonna factor 12 out. This means x cubed minus x squared minus x plus 1 equal to 0. So this means x minus 1 squared, x plus 1 equal to 0, isn't it? Okay, so we have two critical points. So critical points, x equal 1 and x equal negative 1. Isn't it? Yeah. We have the equation as well for the second derivative. So then what we can do actually is evaluate the second derivative at x equal negative 1. What do we get there? 36 plus 24 minus 12. This is positive. So x equal negative 1 is a log minimum. Log minimum. Because the second derivative at that critical point is positive. There. The second derivative at a critical point C is positive. Then the function has a local minimum. Do you understand? Okay, what about f prime at positive 1? F double prime at positive 1. Well, it's going to be 36 minus 24 minus 12. That's clearly negative. Thus, x equal 1 is a log. Log? Equal to 0. Sorry. You're right. Good observation. See, I'm a little tired now. But so x equal 1, we don't know. Okay, the test here is inconclusive. As per the third situation there. The test is inconclusive. F may have a log min there, a log min, a log max, or neither of the two. Well, that's actually the situation. Remember the graph of this function. Down there, x equal negative 1, log min, second derivative at that critical point is positive. X equal positive 1, the function has a saddle down there. Now look, the function at that point is sad. Before hitting 1 is sad, and then it's happy. So here you have an inflection point actually. But it's not a minimum, log min or a log max. It's just an inflection point. Okay? Well, part B here is just an exercise for you to try it, okay? So exercise, find log min, minima, and local maxima for the function f of x equal, what was it? Sine squared of x on the entire real line. So what are you going to do? Well, compute the second derivative. Well, first of all, you're going to compute f prime of x, right? And that's 2 sine x cos of x, right? Well, but 2 sine x cos of x, this is the sine of 2x. Right? So now the second derivative is much easier to compute, right? Because now you have 2 cosine of 2x. That's the second derivative. So what are you going to do? From the first equation, you equate it to 0, and then you need that 2x be equal to the zeros of the sine function. Well, the zeros of the sine function happen at k pi. K pi, right? So k pi, well, n pi must be equal to 2x. So xn is n pi divided by 2. Those are the zeros of f prime. So those are your critical points. Well, those are exactly the points of min and max of the sine function. The sine function looks like this. So you're going to find these points, these points, these points, these points, all of those points. It's fun, much fun, so do it. And then each such point you evaluate here, you determine whether that point yields f double prime 0, positive or negative, and you classify them. Okay? It's all down here anyway, but try to do it. And I think that's everything for today. Just a little summary down there. So what happens if the function is differentiable? The function looks like a smooth curve. Okay, so we're going to focus on that kind of curve down there. If f prime is positive, then the function is increasing. If f prime is negative, the function is decreasing. So the derivative, the first derivative, has to do with whether the function is increasing or decreasing. That's called monotonicity. Okay? So a function, let me tell you, definition and I'm not here. A function which decreases or increases on a certain interval is called a monotonic. Is it monotonic or monotonous? I forgot. I think it's monotonous. Monotonous function. Monotonous function. So monotonous means you are increasing or you are decreasing. That's all. Okay, don't worry too much about that. It's language. I didn't want to go there, but that's the idea. If it's increasing or decreasing, it's called monotonous. Now, not all the functions are monotonous for sure. Okay, you have strange functions that look like well, I don't know. Like what? Yeah. If a function is increasing or decreasing, it's called monotonous. Okay? Alright? And then you have like to determine monotonicity, you just need the first derivative. If the first derivative is positive, the function is monotonous, increasing. If the first derivative is negative, the function is decreasing. Okay? Now, the second derivative tells you about the concavity of the function, how happy or sad it is, right? Second derivative, where is it? Negative, the function is concave down, so sad. Second derivative positive, you have a happy function actually. Now, when f prime changes sign, that's the first theorem we visited today. When f prime changes sign, the f has a local maximum or a local minimum. Okay, so if before hitting down there, a critical point, the first derivative is positive, and then past that point, the first derivative is negative, you have a local max. Okay, and vice versa. And then the second derivative test tells you whether the function is concave up or concave down. If the function changes their behavior, then you have there an inflection point. That's a summary about pretty much everything we have visited today. It was a very let me turn the lesson